Hi, my name is Ida Shum, and I will be speaking with you today about the batteryless nanoenergy harvesting device that was invented at Lawrence Livermore National Laboratory. To set the stage, the current market of microenergy harvesting systems primarily generates electrical energy from various sources such as solar, vibration, thermal, and human movements. This energy can be utilized for powering low power kind of sensors, as well as wireless sensors and electronic device. The existing energy harvesting techniques that we commonly see are in the area of photovoltaic, such as solar and light absorption, thermoelectric, basically taking advantage of thermal gradients or temperature changes, as well as piezoelectric, looking at conversion of mechanical strain to electrical, and electrostatic, which is or capacitive energy harvesting. So each of these existing energy harvesting techniques have current disadvantages, such as low conversion efficiencies, as well as large voltage requirements that cause issues with power management. So what we want to look at in particular is the nanoenergy harvester device that was invented at Lawrence Livermore. The key advantage of this technology is the conversion of chemical energy into electrical energy. Lawrence Livermore has made this nanoenergy harvester using one-dimensional semiconducting nanowires. And so this was one of the areas that was not listed in the previous list. We want to take advantage of the interaction between chemical species and the semiconducting nanowire interfaces. But this induces an electrical potential between the two ends and allows us to take advantage of energy conversion. So we want to take a look at some of the applications, which we'll get to later on, but just to summarize, these can be used in industrial settings as well as building and home automation. There are various application areas that you could take advantage of, such as homeland security, national defense, aerospace, automotive industries, as well as in the area of consumer electronics and medical devices. I'm going to get into the form factors that are listed here. There are two distinct form factors that I want you to look at. On the left is the vertically aligned single crystal zinc oxide nanowires. And you will see that the zinc oxide nanowires are the black lines that are protruding from the pink, which is a PVC. So these nanowires grow about 6 to 7 microns, and they have a density of about 30 microns squared. And you can see the microscopy image in C. So after the growth of this nanowire forest, we infiltrate it with PVC, and it's etched with oxygen plasma to expose the ends. And once the ends are exposed, we can then run some experiments. And these experiments basically involve the use of putting a thin layer that you see in gold of a gold titanium film, as well as a silver paste in which we use to create an electrical contact. And for the experiment, in which we'll get into the next slide, we're essentially dripping certain chemical species onto the device surface, and we monitor the electrical voltage change. On the right-hand side, we have a different form factor, which uses randomly aligned boron-doped silicon nanowires. These silicon nanowires have diameters of around 30 to 55 nanometers, and the lengths are around 10 microns. And you can see the microscopy image of these silicon nanowires in D. So similarly, if you look at the gold bar there, the gold titanium film is resting on top of the exposed silicon nanowires. And from there, we have electrical contacts on both ends, and you can expose the area of the exposed silicon nanowires to the chemical species, and we are able to detect changes. For the device testing, the various form factors that we saw, we've tested various chemical species listed in the table here. You will see that we've made some tests with ethanol and water, acetone, as well as chloroform. And from there, you can see the measurement of the open circuit voltage that was shown or evidenced in each of those experiments. So essentially, these nano devices take advantage of the unique interaction between a chemical species and the surface of the semiconducting nanowire. And this interaction essentially stimulates an electrical voltage between the two ends of these devices. And once these chemical molecules attach to the surface, which you see in the picture on the right-hand side, they induce a change in the charge distribution and on the nanowire surface. And this change essentially produces a voltage between the ends of those nanowires, and which allows us to generate that measurable electric signal. So some of the potential applications, we'll get into sensors in the next slide, but there's military applications in which we can use it to detect chemical and biological weapons, as well as potential medical uses such as pacemakers or insulin control systems. One of the advantages that utilizing a chemical conversion to electricity would be advantageous because existing pacemakers rely on lithium batteries. And these lithium batteries often need to be replaced within 5 to 7 years. And often that replacement creates problems because that patient will be exposed to potential infections. And with longer lifespans, and that could also create a problem with additional or multiple surgeries. The next area that I want to highlight is in the energy space, where we can take advantage of piezoelectric voltages and current outputs, which will enable the powering of consumer electronic devices, such as cell phones and smartphones and tablets that we currently see. So one specific use I do want to talk about is the batteryless sensor, utilizing the semiconducting nanowire array. Current batteryless sensors, they do harvest environmental energy, and we use them to detect chemical and biological agents. The current problem is that these sensing platforms require an external power source, such as a battery, to operate. And oftentimes, this results in a much larger dimension. And so you've lost that advantage of having clandestine applications. And so one of the solutions to that is utilizing this ability to harvest energy from the surrounding environment. So these are some of the advantages of the batteryless sensor using the Lawrence Livermore developed Nanoenergy Harvester. The key is that it converts chemical energy into electrical energy. So if there is a free-floating ethanol molecule or any chemical species that it can convert into electrical energy, that can be used to power the device. So this in turn leads to the elimination of an external power source, such as a battery. And in this case, you can reduce the bulk and the weight. The nanosensor in this sense also responds selectively to a variety of organic molecules. In that table, you saw that there was ethanol. And what we also found out was that there is a dissipation of electric voltage which is unique to each chemical species. And in the testing, we also found that the response times were very fast, in roughly a second. And lastly, this device can also take advantage of heat from the surrounding environment, and that can be used to power any detector. So here are some of the opportunities. We are looking for partners to develop in the areas such as for medical uses, as well as environmental monitoring. We are seeking anybody who's interested in partnering on a collaborative research and development project, as well as these technologies are available for licensing. So we've filed 2 different patent applications, which you see here. And this is also a picture of the scientist, Dr. Morris Wang. And this is my contact information. If you have any questions, feel free to contact me. Thank you.